Alright, so you should have your MakerChip session up. You should be ready with your lab. What I want you to do now is in the upper right hand corner of your MakerChip window there's a button, Save as New Project. So go ahead and click that. That'll save your, that'll give you a URL for your project that you can revisit. So after you do that, bookmark your URL so that you can return to your project if necessary. Alright, so as I said, for the remainder of the labs, you'll be completing the missing logic expressions. Again, always look at your log first before anything else. Make sure your log is clean. You might have warnings there that suggest issues that need to be resolved that'll be confusing if you're looking at your simulation. So clean your log first. As you go through these exercises, initially your simulation is going to report failure. Your CPU is not completed yet. It's not functioning properly. Once you complete all the labs successfully, you'll see that the simulation reports that it passed. And incrementally you'll see the behavior and the visualization looking more and more like the behavior that I demonstrated to explain CPU architecture. Waveform, if all goes well, you won't have to use the waveform window too much. If you do need to use it, you can see signal level, everything that's happening, and use that to debug your design. All right. So now let's, before you actually do any of these lab exercises, let's talk a bit about the language syntax. In fact, I'm going to go back and we'll do that inside the main makerchip.com. And if you'd like to play around as well as I talk through this, it'd be a good idea to go to makerchip.com as well yourselves and listen to what I'm doing. Don't get distracted by playing around, but you can pause the video at any time and try something yourselves. So go ahead and launch the MakerChip IDE. And let me just code up some simple logic expressions. So again, I'm going to arrange my desktop in a convenient way. I want to see the logic diagram and the waveform and my build log. And I'm going to make this a little bit bigger so it's more visible if you guys are shrinking this down in your videos. One more. Alright, so let's just try some simple logic expressions. So all the signals in TLVerilog start with a $sign. And I'm going to start by coding a very simple expression. This is for an inverter. So an inverter is going to take the input signal, which is 0 or 1, and flip it. So let's just say out equals not in. And I'll compile that and simulate it. And we will see a warning in the log saying that we have a signal called in that we're trying to use, but we haven't declared that signal. We haven't assigned that signal to anything, so it's dangling. And if we look at the nav TLV, we can see the highlighting on the input signal saying it's used, but it's never assigned. And similarly, the output we're not using anywhere, so it's assigned but never used, so why do you have this expression? We get a reset signal, which we're not using reset in this logic, so same thing there. But this is all okay. These are all warnings and non-fatal error messages. The environment, recognizing that there's a dangling input, is conveniently going to drive random stimulus on that input for us. And we can see that in our waveform. So the input signal in our waveform is receiving random values, and we see the output is the inverse of the input. So our logic gate worked. And we can do other logic expressions. So we could do in 1 and in 2. And compile that and simulate, and we should get a waveform that will show us 2 input signals and an output signal that's always asserted only when both input 1 and input 2 are asserted. And so here's our waveform. We have in 1 and in 2. Oops. In 1 and in 2. And we can see that the output signal only asserts when both inputs are asserted. So many of you are probably familiar with Verilog already. Many are not. For those of you who are not, there are various operators. We can do OR expressions where the output will assert only if, will assert if either input is asserted. I'm trying to think what else we use in this. It's mostly ands and ors. We can also operate on vectors, bit vectors. So, the instruction, when we load it, just back over here in our CPU core, right? Our instruction, I think, is maybe here. Right? This is a vector of 32 bits. So we can operate on vectors by specifying a width of bits. So I'll do an expression on a 32-bit value. So we can take an input expression that's also 32 bits, and I guess I will OR those bits together. So previously I had an OR that was a Boolean operator, which is 2 bars. To operate on a vector, it's actually a single bar. And you can actually just use expressions that are always single bar, because that works on single bits as well. So if we zoom in now on this expression, in the waveform, you're going to see values that are in hexadecimal. Hexadecimal hopefully is familiar to most folks, but if it's not familiar to you, it's not a big deal. In all likelihood, you're not going to need to interpret the values too much in the waveform. And I'll talk about hexadecimal in a minute. Yeah, so basic logic expression syntax. Let me jump back to the slides now, and I've got a little cheat sheet here with the various operators in Verilog. So we did the OR, we did, well, I didn't do an addition. I can do an addition instead of an OR. You've got bit shifts, comparisons that will compare all of the bits and see if they're equal or not all equal. We've got bit extracts, so if you need to extract a field, which we'll be doing in the tutorial, from a wider vector of bits, you can use this syntax to extract those bits. You can concatenate bits, so if you want to take 2 individual signals, concatenate them together into a single vector, which we'll also be doing. And then there's this really goofy syntax, I don't know who came up with this one, for replicating bits. This, of course, is inherited from Verilog syntax. So if you have a signal, as we'll use it in this tutorial, a single bit signal that you want to replicate some number of times, so taking a Boolean and forming a vector out of that, a field of 1s or 0s, you can use this syntax to replicate sig some number of times. Alright, of course you can use parentheses to group sub-expressions. And if you need to refer to that cheat sheet anytime in the tutorial, you can go back in the video. Also, you have constant expressions. So if you want to express a constant bit vector, you can use this syntax. So this syntax is 3 fields, or 3 parts. First is the number of bits in the vector. The second part, so that's separated by a tick. That's the single quote tick mark. And then a either binary, decimal, or hexadecimal, B, D, or H. We're always going to use binary numbers in this tutorial, so always tick B. And then the binary expression, so a field of 1s and 0s. Yep, so I may as well do that in my MakerChip session. So if I wanted to OR this with a constant expression, I can do a 32-bit binary 1001, and that'll OR with that constant.